we continue our DNA isolation procedure, and we come to part 4. And so in the previous 3 parts, here's what we've done. We have articulated the way that the cell can be lysed, how the lysate can be cleared by neutralization, and how the lysate can be cleared by phenol, chloroform, and isoamyl alcohol extraction. And now that you have a semi-pure lysate for DNA isolation, now in part 4, we're going to look at what do you do to purify that lysate using cesium chloride gradient centrifugation, ethanol precipitation, and column purification. And so the learning objectives are we're going to discuss the principles that underlie the 3 procedures that we're going to look at to purify the cleared lysate, and that is cesium chloride centrifugation, ethanol precipitation, and column purification. We begin with cesium chloride centrifugation. We have discussed this previously in our DNA replication lecture. But basically what it is that if you mix a DNA solution with a cesium chloride salt solution and you subject that to high centrifugation force, let's say you spin it at 100,000 times G for 12 to 24 hours. What's going to happen is that cesium chloride solution is going to generate a density gradient ranging from large or high density on the bottom to low density on the top. Now, since you have a DNA solution that is mixed in there, the DNA within that solution is going to find the gradient at which its buoyant density is equal or identical to the density of that layer, and it's going to settle in at that layer. Now, normally what we do is, in the old days, you would add Ethanol bromide solution to that at a final concentration of 0.5 microgram per mil, in order that after you centrifuge it in a sealed tube, you're going to have different bands. And so here's a picture of what the bands look like. And so you have the RNA is going to be pelleted on the bottom toward one side of the tube. You're going to have followed by plasmid, which is the largest or more distinct band, followed by chromosomal DNA, and followed by protein toward the top. And since you add Ethanol bromide to this solution and you use ultraviolet light, you're going to see a fluorescent RNA pellet, fluorescent DNA band that is very prominent, and a slight fluorescent chromosome DNA band. So all you have to do is use a syringe with a needle, and you plunge that needle in here and you suck out the plasmid DNA. You extract the Ethanol bromide, and then you can precipitate that DNA out, and that DNA is pure. So this is the principle of cesium chloride centrifugation. Ethanol precipitation, as we say, you can precipitate the cleared lysate as well, and that is you add sodium acetate to it at a volume of 1/10 of the total lysate volume. Let's say that you have a lysate volume of 1 mil. A 1/10 volume of that is going to be 100 microliters. So you add 100 microliters of 3 molar sodium acetate, and you mix it nicely, and then you add ethanol at 2 to 2.5 volumes of the total volume of the lysate plus the 1/10 volume of sodium acetate. And so this is 100% cold ethanol. So after you mix it, you incubate it at -20 degrees for 15 to 30 minutes. And then if you're using a microcentrifuge tube, then you centrifuge that tube at high speed in a microcentrifuge at 13,000 times G for about 10-15 minutes at 4 degrees. And then you remove that supernatant. The pellet is going to be on the bottom. Remove the supernatant by aspiration. And then you mix in 70% ethanol. And this is called aqueous ethanol, because it's 70% ethanol and 30% water. And you resuspend the pellet, and the pellet is not going to be resuspended very well, but you add the 70% ethanol, resuspend the pellet as much as you can, and then you spin it again. And then when you remove the supernatant, you let the pellet dry out. You're going to either use a vacuum or dry it by opening it up at room temperature and leaving it for an hour or two. Right? Now, what is the purpose of this step? Well, I think, as you all know, sodium acetate is added, and sodium is going to be dissociated from the acetate. And sodium should actually combine with the DNA to neutralize the negative charges. And once you neutralize the negative charges, DNA can fall out of solution. However, because it is an aqueous solution, the lysate is aqueous, and when you add the sodium acetate, even though there's complete dissociation of sodium from the acetate, sodium does not interact with the DNA. Instead, the sodium, which is positively charged, will interact with the negative charge on water. And the reason for that is water has a dielectric constant, and it's going to be competing for the plus charge on sodium, and it's going to win the competition. The competition is between water and DNA, and really there's no competition at all. Hands down, water is going to win. So sodium is going to interact with water. The negative charge on DNA is still going to be negative charge, and so DNA will remain suspended in that solution. However, once you add 2.5 volumes of 100% ethanol, you are now diluting out the water in that lysate. Now, ethanol has a lower dielectric constant, which means that it can actually allow sodium to interact with the DNA. And once the sodium interacts with the DNA, that neutralizes the negative charge on the DNA, and DNA falls out of solution. And so ethanol precipitation is made possible by the low dielectric constant of ethanol, which allows the interaction of sodium with the DNA, and that allows the DNA to fall out of solution to speed up the precipitation. The 70% ethanol wash is simply used to remove the salt from the DNA, so that when the DNA is precipitated, it is DNA, and no salt is found, or no salt is contaminating the DNA sample. And this is just what we're talking about. Dielectric constant of water is much higher than the dielectric constant of the ethanol. Okay, and so water will interact with the DNA, with the sodium, and DNA will remain suspended in solution. And this is according to Coulomb's law. However, when you dilute the water molecules out with ethanol, ethanol has a lower dielectric constant, which will allow the sodium to interact with the DNA, and thus neutralizing the negative charges on the DNA and allowing the DNA to fall out of solution. And that is the process of DNA precipitation. The third method that can be used to isolate DNA from the cleared lysate is this, that usually the lysate is mixed with a binding buffer, and then it is loaded onto a column that consists of silica beads. Now, silica is negatively charged, and this is what's shown right here. So you have silica right here that is attached to a solid support, and it is negatively charged right here. Now, in the absence of the DNA and salt, water will actually interact with the negatively charged group on silica. However, in the presence of salt and the DNA molecule, the salt is going to be used as a bridge between the silica bead and the DNA to anchor the DNA to the silica bead. And once it anchors that DNA to the silica bead, it's not going to go anywhere. So when you add that, the binding buffer, and you add the DNA solution to the silica bead, the silica will grab the DNA and hold on to it, and you can actually wash several times to remove all kinds of impurities. Now, how you elute that is that when you add water, you are diluting out the competing the sodium with the water, and so now water interacts with the silica bead, and it will free the DNA, and DNA is going to be eluted off of the column. And so the three ways that you can purify that DNA from the cleared lysate is by ethanol precipitation, and let me go back right here, by cesium chloride centrifugation, by ethanol precipitation, or by using a column. And column isolation of DNA takes these days less than 15 minutes. And so this is just a picture. There are a lot of kits that are offered by a lot of companies. And what you do is you basically start by lysing the sample, adding the lysate or neutralizing the lysate, because you usually lysate in alkaline buffer. And so you neutralize that alkaline lysate, you spin that out quickly to pellet all the impurities or precipitates that have precipitated from the neutralization solution, and then you add that clear lysate to the column and you bind it to the silica. You wash the column several times, and then you elute the DNA off in a brand new clean tube with water. And so the next and the final part of this DNA isolation will be part number 5. And when we come back, we're going to talk about how you purify chromosomal DNA. We've talked about how to purify plasmid DNA, but in this section, we're going to talk about how to purify chromosomal DNA.